Back, everybody. Today we are going to talk about absolute convergence. Now, believe it or not, we're actually on the rear end of our study of tests for series. So we will be studying the topic of absolute convergence, and then we're going to be talking about a couple of more tests for convergence, and then we're going to be off to talking about power series. That's the last part of our infinite series unit. Okay, so absolute convergence, what do I mean by that? Let's go over a couple of definitions and then we'll do a couple of examples. So a series is absolutely convergent if the sum of all of our terms when we take the absolute value of them converges. So this means that if I have some alternating series, maybe, this is where the absolute convergence really comes in handy. If I have an alternating series like this, well, what the test for what absolute convergence basically says is if I move all of these guys up, I take the absolute value, move them all the way, and I move them all up, is this going to converge now? So this is what absolute convergence says. So we have a sum, we have a sub n, and then we are going to move that, and then we're going to be testing the absolute value. And if that converges, then this will converge absolutely. So then we also have conditional convergence. So a series is conditionally convergent if it converges but not absolutely. So there might be sometimes when we have this a sub n here and this diverges. In that case, we might need to fall back on some other tests because just because a series diverges if we take the absolute value, that doesn't necessarily mean it's going to converge. Or that doesn't necessarily mean it's going to diverge, it just means it diverges absolutely. So we're going to look at some other tests in that case. Then finally, if we have an absolutely convergent series, then we are going to have a convergent series. So if the absolute value of a sub n converges, then so does the rest of our series. Okay, so let's do an example. Here's one. So determine if the series converges or diverges absolutely or conditionally, right? Okay, that's a very unsurprising problem statement that we'd have here. So the sum we want to look at is the sum from n equals 1 to infinity of -1 to the n plus 1 power over n cubed plus 1. Okay, now this looks like a pretty nasty series. We've got this alternating bit up here, then we've got this cubic in the bottom. Now what we want to look at first is the absolute value. So we're going to take the absolute value of the series because that's going to deal with that alternating term, because absolute value of -1 is 1. So the absolute value of a sub n is the absolute value of -1 to the n plus 1 power over n cubed plus 1. And the -1 to the n plus 1 power, well, that's always going to be 1 when we take the absolute value. So we just get 1 over n cubed plus 1. Well, that's easy. So now let's look at the convergence of this guy. So we have 1 over n cubed, but then we have plus 1 here. So we're going to want to actually use the comparison test because we know of a p-series that's 1 over n cubed, but we need to make sure that all of our terms are less than that. So we know that all the terms 1 over n cubed plus 1 are going to be less than 1 over n cubed. That makes sense intuitively as well. And so we know that 1 over n cubed is a p-series, and our p-value here is going to be 3. So thus, we have the sum of 1 over n cubed, and that's going to converge because we have a p-series with p equals 3 that converges. Okay, so now we also have determined up here that our series, our absolute value series here, is less than this 1 over n cubed. So if we're less than a series that converges, then we're also going to converge as well. So thus, our original series, the sum of 1 over n cubed plus 1 converges by the comparison test. And thus, the full series here, when we take the absolute value of it, is convergent. Thus, it is absolutely convergent. Thus, the series converges. Okay, so that's a pretty standard example about absolute convergence. Now let's look at another one where we might need to use conditional convergence. I don't know. Determine if the series is conditionally or absolutely convergent. Okay, so the sum we want to look at right now is the sum from n equals 1 to infinity of -1 to the n minus 3 over the square root of n. Okay, so we are going to take the absolute value of this guy, And when we do, again, our little alternating term is going to go to 1. So we're left with the sum from n equals 1 to n, or the sum from n equals 1 to infinity of 1 over the square root of n. So now we can see that this is another p-series, but in this case, we can rewrite this as the sum from n equals 1 to infinity of 1 over n to the 1/2. So we have a p-series, but our p-series is 1/2. So we have a p-series with p equals 1/2. That means that it diverges, because if you recall, the p-series only converges when our p is less than 1. So thus, we're going to need to look at a different strategy. So now we are going to look at this guy still, but now we are going to use the alternating series test. So it should be obvious that this satisfies the alternating series test. The alternating series test says if we take the absolute value of this and then we determine that all of them are decreasing, we can take the limit as n goes to infinity and see if it equals 0, and if it does, then it is convergent. So b sub n equals 1 over square root of n. So we're going to take the limit as n approaches infinity of that guy, and well, that should be obvious that it's going to be 0. This guy's going to get close to infinity at some point, and when we divide 1 by infinity, we get 0. So thus, the series is convergent by the alternating series test. Thank you guys for watching. We'll see you